Good afternoon. I'm Brian Wilson. I'm the Executive Director of the Energy Institute at Colorado State University, the Director of our Powerhouse Energy Campus. I had the pleasure of spending 4 years as a Program Director at RPE, and then another 3 years as a consultant to the agency. So I'm a big fan of technology solutions. When Bill Ritter and I launched the Natural Gas Symposium, which is the predecessor to this event, in 2011, it was to really explore the challenges around oil and gas production and to have a really rational dialogue. But one of the things we decided is that if we were only wrestling with the challenges, we wanted to create a sense that there are solution options, and many of those involve technologies. So we've, for the last several years, we've had these technology panels to give you a little bit of flavor of the technologies that are emerging to address some of these major societal issues, and to create a sense of optimism that solutions are possible. So the format for this is that these are really sort of a lightning round of presentations. We'll have a series of 5-minute presentations on the technologies. And then after we do these 8, then we're going to quickly shift, and we've got another 8 presentations, quick set of presentations. But anyway, it does give you a sense of the not only solutions in general, but specifically what's happening in Colorado to address these issues. I'm not going to go into detail on the background of the speakers. Those are in the program and on the apps. So without further ado, we're going to begin. And our first speaker today is Kurt Barth from Colorado State University, talking about solar energy.
Thank you, Brian. So my name is Kurt L. Barth. I'm a director of the NSF-supported Next Generation Photovoltaic Center. And I've been involved in photovoltaics research and commercialization now for over 25 years. And it's in my opinion that it's the most exciting time for solar right now. You can see over the last 10 years that we've experienced almost exponential growth in solar deployments within the U.S. We're between 2016 and on into the future, we're over 10 gigawatts a year deployed in the U.S. Put that into perspective, that's something on the order of 8 to 10, power equivalent of 8 to 10 Glen Canyon dams every year that we're adding just on solar. 60% of the U.S. solar industry is utility scale power. That's not the residential rooftop or commercial. These are the large fields that are deploying to utility assets. Solar was almost 30% of all new electrical capacity added last year. The reason for this is significantly dropping costs. Since 2009, you can see that solar power has dropped almost 10x. Over the course of that time, and that's really fueling this significant growth. So solar is economic right now, unsubsidized, and the Wall Street analyst firm Lazard is a technology agnostic. They analyze different technologies, not just solar, and what they've done is looked at the different technologies and pulled out the different subsidies that are associated with each of the technologies and assigned an energy cost, so-called levelized cost of energy. And you can see that the thin film utility scale solar is the cheapest compared to any of the conventional resources. So I want to say this another way, and this is something that's been highlighted at this conference, and I think we understand this, but perhaps those outside this symposium don't realize that for new generation, if coal, oil, natural gas, or nuclear are used, you're paying more money than solar or wind. And that's not accounting for the benefit associated with greenhouse gas mitigation or pollution prevention. This is just purely dollar per electron. So the question is, okay, solar's great, it's economic now, but the sun doesn't always shine. What happens when we have the peak demand which doesn't fall well when the solar demand, when the solar resource is maximum. Well, we're starting to see with the technology innovations in both solar and storage that solar plus storage now is economic. And with a coal at a median cost of energy at about $101 per megawatt hour, you can see that solar plus storage with the different technologies are right in the game there. An example of this was also brought up, I think, by Governor Ritter earlier this session, was that in 2018, Xcel put a power plan to the PUC in which they wanted to retire coal generation and add significant wind, solar, and storage. The outcome of that plan would be to save customers over $215 million and cut carbon emissions in half. So the next generation technology that I work on holds opportunity to be even cheaper still. And this is an example of a cadmium telluride thin film plant deployed in Arizona. You get a sense of the scale there. The structures to the right are not cars, those are buildings. This is a giant facility, but this is not something out of the ordinary. There's multiple of these facilities added every year. Case of how economic this is, Arizona Public Service asked for power generation between 3 and 8 p.m. It was open to any technology. The cheapest technology, the cheapest bid was solar plus storage using thin film cadmium telluride. The center that I'm with is the Next Generation Photovoltaic Center, is at the forefront of this next generation technology in solar. We started in 1991 researching this technology where we chose to look at that technology based on the fundamentals. It wasn't something that was an outcome of a particular grant activity. It was a key effort that we chose to look forward. And now our center is one of the leading ones in all solar and one of the leading technologies development areas for thin film. We have multiple domestic and international universities and partner with the Department of Energy, the National Science Foundation, and Syndia. We do research across the technology readiness levels from the most abstract basic R&D up to technology commercialization. Our contributions include large-scale commercial demonstration in manufacturing. We hold the record amongst university and national labs for our cell technology, and we're working with a new advanced architecture for protecting the module in the field that's received collaboratory support. This is a picture of a commercial manufacturing plant that was a spin out of our tech. Thank you, Brian. So our next step is to improve efficiency, go to a more simple module design, and lower costs. So I'll leave you with our center mission and the power of the sun to make PV electricity a major source of energy. Thank you.
Our next speaker is Sybil Charvel from Colorado State University. He'll be talking about conversion of organic materials into fuels.
Oh, okay. All right, thank you very much. And I'm gonna just go ahead and jump right in here. I'll be talking about how we can treat waste materials, particularly organic waste materials, anaerobically to generate value-added products, including fuels. The most classic example of this kind of technology is anaerobic digestion, which has been around for decades in wastewater treatment facilities. And with this kind of technology, we can take food waste, we can take animal manure, human waste, any waste material that's organic in nature, and use microorganisms to convert that organic material into methane. In the last breakout session, there was some talk about food waste, and obviously the elephant in the room with food waste is generating less. Some municipalities, up to 40% of their food waste is total waste material is made up of food waste. So that's too much. We've got to reduce food waste, but as long as humans are around and eating food, we're going to have some food waste. As long as we're eating meat and animal products, we're going to have cows and pigs and things pooping, and we've also got human waste to deal with. Okay, so this is a way that we can take that waste material that's existing and convert it into something valuable. Okay, so this goes through the anaerobic digestion process, and I'm not going to go through all these steps. The important thing here, at the bottom there, you see the methane. This is all the biological processes. One thing we can do is actually cut this process off before methane is generated, and then we form these organic acids. So we actually inhibit the methane generation and instead form these potentially higher valuable organic acids and carboxylic acids that can be used as fuels or to make plastics. Methane is not right now financially highly valuable, so this can be a way that we can modify this technology to make other more valuable products, and there's a lot of ongoing research there. Question comes up, is this really decarbonization? We're still using carbon and there's going to be emissions. If we go and take this methane and put it in an engine, we're going to make emissions, and we're maybe not necessarily reducing carbon. We did a case study in the city of Fort Collins. It was a life cycle assessment that looked at carbon footprint. There's two categories here, and you can see in blue is the anaerobic digestion, or AD, green is composting, and red is landfilling the waste material. And you can see in terms of fossil fuels, there's an actual sink of emissions or use of fossil fuels that results from anaerobic digestion and composting, really, even when we consider the emissions. And a lot of that is because we're producing a fossil fuel that's replacing, or we're producing a fuel that's replacing fossil fuels. And then a large component is that the digestate can serve as a soil carbon storage, reducing carbon, and these also can replace nitrogen. So these food waste and all these waste materials have a lot of nitrogen and phosphorus that can replace synthetic fertilizers, and there's a lot of fossil fuel benefits from that as well. Even when we don't consider those, anaerobic digestion still has a lower carbon footprint overall compared to landfilling. Okay, so there's lots of ways we're working to make new technologies that can work on anaerobic digestion or generation of these other valuable carboxylic acids. My lab has generated a technology that's been licensed by Nexus Bioenergy. Traditionally, anaerobic digesters were in wastewater facilities where wastes are very wet. And we're working really to address some of these higher solid content manures, like what's generated on feedlots here. So this is the technology that we've been working to develop. This is how this can, let me go back real quick, because important here is that we're also working on capturing fertilizer, capturing every potential resource. I think most important point moving forward is we've got to work to make these systems more efficient and capture every possible resource out of these waste materials and turn those into value-added products to make this work. And that's where a lot of the innovation is happening right now, is in how we can generate those useful products. And this is just a picture of a potential regional biodigester where you could have it collecting waste from different sources, like I've talked about, municipalities, feedlots, any of the above. And with that, I'll go ahead and conclude.
Thank you, Sybil. Our next speaker is Gregory Kerr from University of Colorado, who's going to be talking about some really cool laser sensors that they were developing.
Excellent. Thank you so much, Brian. So I hope in the next 5 minutes I can get you excited about the work that we've been doing to take Colorado's very own Nobel Prize winning, laser technology. That was the whole talk, done. And it's gonna be a little, okay, start that over again. All right, how we can take and leverage this frequency comb laser technology to build sensors that help us to come up with carbon-reducing strategies in the future. So everything I'm going to talk about is based on a simple but unique property of molecules, and that is that every molecule absorbs light at very specific wavelengths, different colors. So if I take light of many colors and I shine it through a region that might contain water vapor, I'm going to see at the other end that some of the light is missing at specific wavelengths. And which wavelengths is determined by the structure of that water molecule. If I change the structure to carbon dioxide, I get a different signature. If I do it again to methane, I get yet another signature. And so the very same thing that makes most of these gases greenhouse gases that absorb, we can turn that around and turn it into sensors to look for these molecules and quantify them very, very carefully. The sensor that I'm going to talk about is based on a special kind of light source, a laser. We all know lasers, very coherent. I can shine them over long distances, over known beam paths. But there's just one problem, and that's that most lasers are one pure color of light. So it's not so good if I'm trying to identify those special signatures of the different molecules. Over about the last 15 years, physicists at the National Institute of Standards and Technology at CU have built a type of laser called a frequency comb that generates hundreds of thousands or even millions of colors of light from the same laser at the same time. And this is powerful because we can start to use this to see those signatures of the different gases. Just one little problem. When I started on this a few years ago as an engineer, we had what was on the left there, a room-sized laser, $500,000, extremely sensitive. And over the coming years, the last 5 years, we've engineered this down into a little 19-inch rack portable system. And that has enabled some really cool new measurements that we can do towards carbon reduction. We've heard a lot about natural gas as a transition fuel in terms of reducing our carbon. It's also a really good load balancer because natural gas can enable rapidly varying electricity generation technologies. And in particular, reciprocating engines, which are giant versions of what's in your car, can come to full load in 5 minutes. And so these are being installed to offset things like wind and solar that ramp very quickly. The issue is that we can't just drop natural gas into a diesel engine like we've been running for years and years. It doesn't burn quite as well, and it burns differently. So we've paired up with Anthony Marchese at Colorado State University, and we brought these frequency comb lasers up to his lab and tried to gain a window into the combustion process that's happening in natural gas engines as it's happening. And so these are some measurements of temperature during the compression in a system much like a large-scale natural gas combustor, and we can make measurements of temperature, of methane, of the evolution of these species greater than 1,000 times per second. So we can take that same technology, we can now move way up to the upstream end of things and look at the production of natural gas. So again, we know that burning natural gas is nice as a transition fuel, but because it's a powerful greenhouse gas absorber, if we leak just a few % of our methane along the way, it more or less offsets the benefits of burning it as a fuel. Also, if we have rare but dangerous accidents, that has caused, as many Coloradans have seen, a lot of friction at that urban oil and gas interface. And so the question that we were asking ourselves is, could we take this same technology, could we send laser beams out over mile-long path lengths and look for leaks across vast swaths of the very dense oil and gas infrastructure that exists, for example, in eastern Colorado? And if we do that, can we bring the monitoring cost per site to really, really low levels? And so we've done this. With funding from Brian and the ARPA-E program, we've put these systems in the back of trailers in eastern Colorado. We've sent the laser beams out over oil and gas fields. We've gone to the CSU METEC test site and shown that we can detect from a kilometer away methane leaks as small as 1/8 of your breathing rate right now. And we can attribute it to the right pad. We can size it to within 20%. And the team got very excited about this, and we've spun out a company now called Longpath Technologies that's working with 4 industrial partners to roll this technology out into the field and figure out how it is that we can integrate this with oil and gas business practices. So we're excited about that, and if you're excited about that too, please email me. We're looking for a new CMO to join the company right now. Thank you.
Thank you, Greg. I think this is just a great example of collaboration between different institutions and how we are stronger working together as different institutions. Our next speaker is Jim Kale from Colorado State University, who's talking about microgrid technology.
Okay, so Jim Kale from CSU, and today what I'll talk about is how hybrid microgrid technology is enabling the transition between fossil fuels to sustainable energy sources. What's interesting about the project that I'll show is that it's actually being developed specifically for oil and gas, but has much broader applications. So to give you some background, there are about 1,000 land-based drilling rigs in the United States, according to the latest numbers. And these are often located in very remote areas, so there's not a typical electrical connection. So these typically are being powered by generators, so either wellhead gas or propane in some cases. And the power delivery challenge here is that the loads are extremely intermittent, large and intermittent. So what that means is that you typically will have to oversize these generators or string a lot of parallel generators together, and they don't typically operate at their maximum efficiency point. At the same time, then, you also have the EPA permits, which is there are costs of doing business, and the permitting price is based on the nameplate ratings of the engine. So there's a lot of incentives to reduce the size of the engine and reduce fuel flow. So what I'll talk about today are mobile hybrid microgrid technologies, which are being developed to solve this problem, with several bonuses. One being that the power quality, the waveforms itself, it's a lot cleaner. In addition, the overall system reliability is improved. It's very important to have that reliability just because in these cases, if those systems go down, it's very expensive to bring back up. So the approach here, technical approach, is the typical generator system in a hybrid combination with energy storage and power electronics. So the idea is that as the load increases, you get these large swells in load, then you can provide power almost instantaneously using the batteries. So that idea itself is not new, but the technical advances that are happening are around the instantaneous tuning and control based on changes in load dynamics. The other thing with this technology is that if the generator system goes out, let's say that there's a discontinuity in fuel flow from the wellhead, then this acts as essentially a UPS. So you can essentially ride through those cases with the battery storage system. So the example that I'll show, a real system, is the reduction of a 22-liter natural gas generator down to an 11-liter generator. And this is the system here. This is our prototype system, 400 kW, which is being developed by Moser Energy Systems. You may have heard of them if you're in the oil and gas industry. And right now, as we speak, we're actually doing experimental validation at the CSU Powerhouse Lab. It's about an hour north of us, if you're interested in visiting. And we have infrastructure there to do testing up to 400 kW with a programmable load bank so that we can do side-by-side measurements between the conventional and the hybrid unit. So steady state, randomized loads, and we have research-grade gas analyzers to do the comparisons. So this is just showing two of the systems here, the 22-liter on the right and then the hybrid unit on the left. So I'll show you some initial data that we've gotten. I know it's a little small, but the plot on the top is their randomized load profiles that are based on, statistically, based on measurements that we've obtained. You can see the spike in the middle where it goes up to about 350 kW. Energy storage seamlessly accounts for that. If you look at the black plot on the bottom, that's showing fuel flow from the conventional system, and the blue line is showing the hybrid system. So there's a clear reduction in fuel flow, and we think there'll be a reduction in emissions as well. So I don't have a lot of time to talk about other applications, but you can think about those drilling operations, like I said, high intermittent power. As you know, we're trying to electrify our shipping ports in the US and elsewhere, so very similar type of application. In addition, in terms of disaster response, if you think about being in a remote area where you're trying to power vehicles, for instance, forklifts and other vehicles for cleanup and other types of responses, then these types of systems can be used. So I guess the ironic thing here is that, as I said, this is being developed for an oil and gas application, has much broader applications as well. So in summary, as I mentioned, mobile hybrid technologies can be used in this case, but can also be used in other applications And business incentives are actually driving the technical solutions here. Lower permitting costs, lower emissions. I mentioned 2 of the applications as well, but also, you may know, but in emerging economies, a lot of times they're powered on 100% diesel fuel. So it's relatively difficult to make the transition to renewable. So we see this as sort of a bridging technology to incrementally get to larger amounts of renewables. So that's all that I had today. If you would like to talk about this project or other research at Powerhouse, this is my email address, and I have the contact for the VP of Innovation and BD at Moser here as well. So thank you.
Thank you, Jim. Our next speaker is Jill Engel-Cox from NREL, the National Renewable Energy Lab, who's going to be talking about their work on systems level analysis.
Great, thank you very much. Very happy to be here, and thanks to Brian and everyone for the invitation. I'm the director of the Joint Institute for Strategic Energy Analysis that's located at the National Renewable Energy Laboratory, and we are a partnership of the NREL plus our colleagues here at the CSU, CU Boulder, MIT, Stanford, and of course Colorado School of Mines. JICEA is all about the integration and systems analysis, and that is not only collaboration with the other universities and multiple industries, but also we were formed to really make that link between renewable energy and energy efficiency and other types of technology. So we work a lot with the oil and gas industry, we work a lot with industry, we work a lot with manufacturing, and our goal is to try to bring these solutions, bring these systems together for solutions. So I'm going to talk about 2 areas today that we've been working on. One related to renewable energy related to oil and gas industry, and the other related to agriculture. So a lot of the things that we've been focused on have been related to sustainable natural gas and oil production. We initially did some work a number of years ago on methane reduction and methane leak reduction, which we've heard a lot about today. We also do a lot around manufacturing and the integration of these types of infrastructures. And so we've put out a series of papers that are on different topics that might be of interest. We've looked at the carbon intensity of crude oil production as well as other types of energy productions, looking at the life cycle land requirements of different types of energy systems. We've looked at manufacturing of polysilicon. We're starting to look at the mining industry now and what type of energy it needs there and how that feeds into our manufacturing supply chains. And then a recent paper, which if you're interested, I have a few copies of, is looking at innovations in the upstream oil and gas industry and that are working closely with communities. So one of the things that we've really focused on is how do you put together consortiums to study specific problems. And this is an existing project we have. We've looked at the electric grid as well as the gas pipeline network, which are not interconnected at all, although they're becoming heavily dependent on each other. As we're getting 30 to 40% of our electricity now from natural gas, now suddenly it's very important how our gas pipeline system works with our electricity grid system. So one of the things that we do is we put together consortiums of partners, and you can see the ones listed here are not groups that normally work together and fund research together. And this consortium we put together to look at how can we co-simulate the power in the natural gas networks. How can we define how those systems work together and figure out how to do day-ahead operations, especially when we're expecting extreme weather conditions. So this project will be putting out some of its final reports in the next few months. So that's then built on how we can think more closely about how industry works. So how do we bring some of these clean power technologies to industrial processes, such as the production of oil and gas? And so currently 10 to 25% of oil and gas is self-consumed in the production, both the extraction, the piping, and then the refining process. So this is a very precious material. With the conversation, some of the presenters this morning were talking about how we're going to need oil and gas for things like aviation fuels and things which you're going to need a highly dense fuel that's going to be hard to do with solar and wind. So how do we conserve these precious resources and not self-consume them or not burn them in a way that's inefficient? And so this is a project that we're starting to put a consortium together now about how we can bring wind and solar and other things into the oil and gas process so that the majority of that product gets used for higher value uses. A second project I want to mention that we're working on is we've been looking at how do you look at the land use and the optimal land use of renewables and other types of energy systems. And we've been looking at how you co-locate agriculture and wind and photovoltaic development. And so we've all seen that under most wind turbines, you get a lot of agricultural development. But now we're actually doing studies of what are the best crops to grow under solar panels. How do you put them at the right height and the right angle so that you still get proper amount of light and water, and how can you actually optimize these? And we've got a number of sites that are actually looking at the best crops, the best locations, the best approaches to do this. So this led us into thinking about these rural areas. There's a lot of focus on urban areas and electricity generation, but a lot of our energy comes from rural areas, either the oil and gas extraction or wind and solar developments. So we're starting to put together a new project that's going to look at economics of rural areas and how we can transform those, thinking about the energy, water, food nexus into best use of improving the lives in these rural communities, because that is where a lot of our energy extraction and energy is coming from. So thinking about these holistically, energy, water, food together, we're seeking to put together a consortium to begin to explore these, both internationally, where there's obviously a lot of energy, water, food issues, as well as our domestic rural locations as well. So thank you very much, and if you're interested in more information about these projects or in joining us to work on them together, I'd be happy to talk later.
Thank you, Jill. Our next speaker is Daniel Steinberg, also from MNREL, who will be talking about energy policy, regulatory, and econometric analysis.
Oh, man. All right, here we are. So yeah, I'm Dan Steinberg. I'm talking mostly about electrification, a little confusion. But I guess I wanted to start off and actually just ask the crowd a question is, how many of you owned, or leased, I should say, a battery electric vehicle or a plug-in hybrid 5 years ago? A few, maybe 10, it's a lot. How about now? How many of you own one now? All right, some more, but not overwhelming. But in any case, we're seeing rapid growth in electrification, and just although this sample of the population may not be representative of the US or indeed the world, you're actually in pretty good company. So this slide shows the percentage of the final energy that's made up of by electricity. So final energy is the stuff that's consumed at the point of end use. So the fuel that's going into your car, the electricity that's powering these lights and the computers right now. And what we're seeing is basically across the board here for this sample of countries and regions, the amount of stuff that's being powered by electricity is increasing. So this is not just increase in electricity consumption, but the amount of end-use services that are being consumed are more and more being powered by electricity. So why is this? I'd argue that it's because electricity is a pretty fantastic fuel. Once you have invested and built a transmission system, you can move electric energy from point A to point B almost instantaneously, about 3/4 the speed of light. It's highly flexible and controllable. And as a result of that, you can use it to power a whole range of end-use services, from HVAC applications, so heating and cooling, to industrial scale processes, in this case an electric arc furnace, obviously transportation services, and of course all your home appliances. Historically, electricity has been something that's been very challenging to store. And as a result, it's required large capital investments in things like pumped hydro storage facilities, shown in the bottom right there, things that require a lot of money, have a lot of environmental impact. But as we've seen precipitous drops in the cost of battery storage, this is becoming much more feasible today. And perhaps of most relevance to this session, electricity has 0 point of use emissions, right? When you consume electricity, there's nothing coming out of your espresso machine on your counter. There's nothing that you're breathing in, it's just electricity. And that's not to say that electricity doesn't have large amounts of emissions associated with it. Of course, here in the US, it accounts for about 1/3 of total emissions economy-wide. But those are large point source emissions, and there's ways that we can mitigate those if desired, through either substitution to lower emitting or zero emitting generation facilities, or through direct capture, which I think you're going to hear a little bit about later today in terms of capture and storage of those emissions. So as a result of the potential emissions benefits, as well as the potential benefits associated with the quality of the service that's available through electrified technologies, so this might be your zippy Tesla that you're driving around, it might be a single air source heat pump, electric fueled air source heat pump that can provide all your heating and cooling needs, as well as water heating from a single unit in your house. Or it might be your new induction range, which can boil water extremely quickly or be highly controllable in terms of the amount of heat you're committing to your pots and pans. We perhaps are on a precipice of rapid electrification of many end-use services. And so one thing that we've been asking is, what are the potential impacts of a future that's highly electrified? How is the power sector going to respond to that? And what are the total economy-wide impacts? So I wanted to share just a few quick results from this. It's a multi-year study, multi-institution study. And it's really a scenario-based approach to the analysis, where we looked at what are the key end uses that could be electrified going forward? What are the different technologies that could provide those end uses, and how are those technologies going to evolve through time? And given that evolution, how might the adoption behavior change? So is it not just a certain subset that's going to be adopting battery electric vehicles, but are they going to be pervasive across the economy? Same goes for the building sector, for the industrial sector. So we developed 3 different scenarios of evolution through time: a business as usual scenario, the reference case shown there, which is basically what it is just business as usual. Things stay relatively similar to how they are today. A medium case, which is basically widespread electrification of all the low-hanging fruit. So this is electrification of light-duty vehicles, electrification of heating in buildings, both residential and commercial buildings. A little bit of industrial electrification, but not widespread electrification. And then under the high case, we're really pushing the limit here, where we're looking at the types of end uses that would likely require some sort of policy or incentive to actually achieve. So this is getting into things like electrifying heavy-duty vehicles, so bus fleets, short-haul heavy-duty transportation. So I want to make a couple key points on this result here. So one is that electrification could really increase the total consumption of electricity. We're looking at rates of growth that haven't been matched since really the mid-century, the mid-20th century, when the power sector was growing very rapidly, only 1.6% per year, but that means a total of 40% increase in total electricity consumption economy-wide. The other key thing is that most of that is coming from transportation. And this is something that we found in our study that's been confirmed across a lot of different studies that different institutions have conducted. But currently, the transportation sector is less than 1% electrified. And so if we start to plug away at that end use, we could really generate a lot more demand for electricity and substituting away from conventional fossils. Right, so what does this actually mean? So we actually don't have emissions estimates, but we'll take a quick look at emissions in the next slide. But here we're saying, what is the change in the actual end-use fuel consumption associated with these electrification scenarios? And for particularly those fuels associated with transportation, gasoline and diesel, we see drastic reductions in the amount of those fuels that are being consumed for those specific end uses, for transportation. We also see pretty substantial decreases in the amount of natural gas consumed for heating purposes and for industrial purposes. So overall, at that point of end use, we're seeing huge opportunity to reduce consumption of these fossil fuels that can then be used for other purposes, be it increased exports, utilization, power generation. Ultimately, what are the emissions impacts of these scenarios? We're still working on this. It's jointly determined by both what's happening at the end use side as well as what's happening on the power sector. Our next phase of the study is really going to be looking at the power sector evolution, and we'll be releasing that shortly. And you can go to this website here for more information, or come find me afterwards. Thank you.
Thank you, Dan. Our next speaker is Kathleen Stacks from Guzman Energy, who's going to be talking about market transformations.
So I'm here not to talk about technology, but when all of the technology is moving in a great direction like we've got going on, how does that benefit the end user, particularly looking at rural communities who plug all of their stuff in and just count on the lights being on, and are in some places seeing their rates continue to go up. And I think one of the challenges that we are seeing is that the utility model, as it's been, is a bit challenging to change, in large part because we've got these very large fossil fuel assets that utilities still owe quite a bit of money on, and that makes it very difficult to retire those assets early, make that transition to renewable energy. Fortunately, you've got companies like Xcel that are finding ways to do that and actually keep rates down for their customers. And so following leadership like that with some of those investor-owned utilities, they've been able to find some very creative solutions. So in comes my company, which is not an Excel. We are a wholesale power provider, and what we're looking to do is help those more rural communities take advantage of this market transition where renewable energy has become cheaper than some of these existing fossil fuel assets. And so this is a sort of a busy slide that kind of shows how this transition has happened over the last few years. So if you look on the left side, you've got just barely over a decade ago, the generation and transmission system was the way to go. Coal was still king. It was before natural gas prices dropped, which you can kind of see in that sort of second column there. And then really starting to see the decline in wind and solar prices. And all of a sudden, the prices of energy is flipping on its head. And it's cheaper to have wind and solar. But again, difficult to implement when you've got fossil fuel assets that you cannot just turn off and shut down. I'm going to walk through a case study that we've done. Kit Carson Electric Cooperative is a rural co-op in northern New Mexico. They serve the Taos area, and they were a member of Tri-State, and this sort of highlights some of their challenges. They had increasing rates. They had a large load that was looking to expand but couldn't have stability or in their expectations for what their rates were going to be the next year. They had a limit on the amount of renewable energy they could build at 5%. They had a community that was really clamoring for an increase in renewable energy. And so they started to explore different options, and they negotiated an exit fee from Tri-State and went out on the market to figure out where they could go get cheaper power. And so here's where we came in and helped them finance that exit fee. And then we are now providing their power. They set a goal for being 100% solar powered in the daytime by 2022. And in order to do that, they needed to build about 36 megawatts of solar with some storage integrated in as well. And we gave them that flexibility. We're helping them locate throughout the community, have tax base. They're doing it in sort of 1 to 3 megawatt arrays. They're using local labor. They're using local businesses. They're building this within the transmission system as it exists, because it's hard to run electricity both ways on the line, and depending on how they're built. So really, ultimately, once they, when all of this is online, they're paying off that exit fee in about 6 years, which means at this point in time, their rates have remained pretty stable. After that 6 years is over in 2022, their rates are going to decline by about 40%. And they are going to be able to hit that goal. They're well on their way. So really, this is a model that we're looking at across the West, looking at both Colorado and New Mexico, to try to identify communities that are looking for something different, that are clamoring for increased renewable energy within their systems and having more flexibility. We serve about 5 different communities right now, and have literally gone into each one of these places and set up a slightly different offering for each one of them, depending on what their needs are. So whether it's increased renewable energy, lower rates, more economic competitiveness. And I think one of the things that's unique about this is that it is pushing a transition that everybody wants, but it's actually taking these steps, and it's enabling ways to take advantage of the cheaper energy to help accelerate the depreciation of some of these larger assets. And it's also we're doing it in smaller chunks. So we're doing it in 10-year contracts. So at the end of 10 years, Kit Carson can go back out on the market and look for cheaper prices, and we can compete for those. But at that point in time, you've allowed for changes in technology and changes in the market in a way that we haven't been able to do in the past in the utility sector. So with that, that's a fast 5 minutes.
Thank you, Kathleen. And our last speaker in this session is Mark Northam, who's director of the School of Energy Resources at the University of Wyoming, who'll be talking about carbon capture, reuse, and sequestration.
Thank you, Brian. And the second part of that is it still a viable pathway to low emissions energy? So let me start with a definition just so we're on the same page. Carbon capture, utilization, and storage are discrete solutions for separating carbon dioxide from flue gas, and now with the discussions about air capture from air, and then manufacturing products or disposing of the carbon dioxide underground as a means of keeping it out of the atmosphere. Let me talk a little about the history of it. The capture side of it really had its birth in the use of amine absorption as a means of sweetening natural gas in the early 1950s. Utilization and storage were really represented, what we've learned about it, really represented by enhanced oil recovery, which became pretty commonplace in the industry in the 1970s with the availability of natural sources of CO2, making it cheap and abundant. Present state of the technology, there are lots of different solutions for capture. There are absorption with solvents, primarily still amine solutions. These have been tested and proven at scale. They have high capital and operating costs, and there are some environmental concerns. Dry absorption is following on after solvents, still typically using amines. There are now research and development on membranes and hybrid membrane absorption mechanisms, and my personal favorite is cryogenic capture, which uses a refrigerant to freeze the carbon dioxide out of the flue gas and capture it in that way. Utilization is still dominated by enhanced oil recovery. In fact, it's the only one that is currently viable at scale. Chemistry of conversion of CO2 to products and to fuels is very difficult, but it is a subject of lots of R&D, and in fact the X Prize organization is running a competition right now to award two $10 million prizes to some successful projects that they've selected, 5 of which are being demonstrated in Wyoming. Storage is focused on geologic formations, saline aquifers, and enhanced oil recovery. The first and most successful of those was implemented in 1996, and I was there. I was part of the team that implemented that. From concept to implementation was a 2-year process. It's been going now for 23 years, storing 1 million tons a year of carbon dioxide. So there are still big challenges with CCUS. Cost is the big one. Our government is implementing incentives, and we are starting to think about business models to make it work. Transport of CO2 is a concern. Of course, there are problems with public acceptance, and of course, end of life of an injection project is still very uncertain. Insurance, liability, post-project ownership are all unknowns at this point. So I want to talk a little, end my comments with trying to convey a sense of urgency. Carbon capture and storage research was initiated by the Carbon Capture and Sequestration Technologies program at MIT in 1989, and I was there as a representative of Mobil Oil. That was 30 years ago. In 1989, the atmospheric concentration of CO2 was 352 parts per million. Today, it's 412 parts per million, a 60 part per million increase in 30 years. Whatever solution to climate change you endorse, renewable energy, electric cars, more efficient buildings, all of the things we've heard about, is going to take time to implement, and especially in non-developed countries. Signatories to the Paris Climate Agreement agree that we must limit global warming to 2 degrees above pre-industrial levels and strive to limit it to 1.5 degrees. 450 parts per million CO2 concentration in the atmosphere is widely recognized as the limit of CO2 concentration that we can tolerate. Projections are that the globe must aspire to net zero emissions by 2050 and then to continue to negative emissions after that. That's 30 short years from now to drastically decarbonize global energy production through all means possible. We have substantially proven that CCS works. It's expensive, but so were horizontal wells and fracking 10 years ago. So was space exploration in the early days, and in fact today. Cost will come down and efficiency will rise, but only with experience. CCUS on fossil energy plants is not a universal solution, but it is certainly a bridge to the future and something that we can do to make progress over the next decades. What we learn from CCUS on fossil energy plants now will apply later to BECCS, which is bioenergy with carbon capture and storage. BECCS will be one contributor to negative emissions. Air capture may also contribute to negative emissions when it's ready, and it is basically CCS on a 350 times more dilute flue gas system. We shouldn't wait for perfections. Further delays to reach the 100% solution will make the final goal of controlling global warming that much more difficult. Global motivation for CCUS is waning. There are more projects being canceled than being new projects that are coming online at this point. I fear that if another decade passes without implementation of CCS projects, we will lose support for doing so, and there will be real implications for air capture and BECCS later.
Thank you, Mark. And another thanks to the entire panel. You get a sense here of that we have grounds to be optimistic. We've got great collaboration here in Colorado and the region, developing technologies, policies, new business models to get those into production. And don't go away, because we've got more to come. We've got another set, and Ryan and his team are coming up right now.